As a next step, I would like to introduce the kinematic control. We have seen that F equal KPE plus KDE dot, and we can insert the found control parameters. In this equation, we can factor out M. We can also divide the whole equation by M, and since we divide the force by the mass, we get an acceleration as the output signal of the controller. We introduce new control parameters, which are the original ones divided by the factor M. This formulation is called kinematic control because only kinematic quantities appears in the equation. To determine a force, we must multiply the acceleration by the mass. For linear motion, we use the mass, and for rotational motion, we use the rotation inertia. In the general case, we have an acceleration vector, which we multiply by the mass matrix to get a force. This is always in generalized robot coordinates. In the control system, we now see a much more flexible formulation of the PD controller. The dynamics and thus the mass matrix of the robot changes constantly, depending on its position. Finding a good control for this variable controlled system would have been a pain. However, since we have now factored out the mass matrix, the most important changes in the robot's dynamic are taken into account in it, and our control becomes simple. For better visualization, we can insert the meaning of the control parameters directly into the control diagram. The result of our efforts is impressive. The system is very clear, and we can design the kinematic controller without knowing much about the robot's dynamic. In most cases, the control parameters are even identical for all robot axes. Since we can specify the bandwidth with the kinematic controller, could we then realize an arbitrary stiff controller? The answer is no. The solution only works as long as our simple mass model for the robot holds true. In fact, this is usually the case if one builds the mechanical structure well in terms of controllability, for example by making the inertia of the robot small compared to the inertia of the motor, and the controller then sees only the motor. However, there is another limit that occurs in every system, which I would like to present here. What prevents us from setting a control bandwidth with 10,000 Hz in our control system? If we look at our controller, the P controller and the D controller each contribute to the acceleration. Let's take a closer look at the Q.ed acceleration. The acceleration Q.ed is proportional to the velocity control error and to the parameter kd. We could also say inversely proportional to a time dt, which corresponds to the time in which the velocity control error would be fully compensated if we freeze the servo acceleration. Since we use digital controls and compute the controller algorithms with a fixed sampling clock, the controller in fact freezes each clock for the duration t clock. If Td is greater than t clock, the speed approaches the target speed asymptotically. If Td is exactly equal to t clock, the control error is compensated in exactly one control cycle. If Td is smaller than t clock but larger than t clock half, the acceleration oscillates widely with a period of 2 control cycles, but the oscillation still decays. If Td is smaller than 0.5 times t clock, the oscillation increases until the controller only jumps back and forth between the positive and negative saturation values. It can therefore be said that the stiffness limit of the velocity feedback is reached when the velocity error is compensated in one single control cycle. It can therefore be said that Kd must never be smaller than the controller cycle for physical reasons. But where is the limit in everyday reality? What is possible? We have assumed that the control is calculated through every control cycle, from reading the sensor to energizing the actuator. But this is not correct. The algorithms need time to be calculated, and often the inputs and outputs are triggered almost simultaneously to have a common time pace. This leads to a time delay of up to 1 control cycle. Further time delays are caused, for example, by the numerical differentiation of the position signal. It therefore makes sense to start from twice the value of the control cycle and to add a small safety factor. In my personal experience, I have found that with a factor of 2, a safety factor of 1.15 is usually already sufficient, which is extremely close to the optimal point. Thus, TD must be larger than 2.3 times T clock, respective KD must be 2.3 times smaller than F clock. We determine omega 0 by dividing KD by 2 times D and get F clock divided by 3.2 for omega 0 under the assumption of D equal 0.7. If we calculate the frequency, we find that the controlled bandwidth F0 is 20 times smaller than the controller frequency F clock. So we found that the frequency of the control bandwidth is 20 times smaller than the clock frequency of the digital controller. Omega is 3.2 times smaller than the clock frequency, both under the assumption that 0.7 is used for Leer's damping measure. The kinematic control constant Kp is as known omega squared and the damping constant Kd is 2 times d times omega. Kd is 2.3 times smaller than the clock frequency. Let's look at an example. The clock frequency is 2 kHz. Kd directly calculated is 470 seconds to the power of minus 1. The controller bandwidth F0 is 100 Hz when using the rule of 20. Kd calculated using omega is 879 seconds to the power of minus 1. Omega is 628 seconds to the power of minus 1. Kp is omega squared and thus 394,000 seconds to the power of minus 2. As a next step, watch the video about advanced robot control and learn about cascaded kinematic controller and controller using the dynamic of the model of the robot. For the implementation, we recommend the open source robotic framework EROS, which we also use in this course. You find it on eros.org or wiki.eros.org. We are happy to answer your questions or suggestions in the forum on Moodle or, if you are not enrolled in the course, in the comments here.